Okay, good.
Okay, I
Great.
can.
Shenming, when Andres gets here, I'm also going to make him, no, actually, you should make him co-host. I can't anymore.
Okay,
Yeah. Oh, actually, can you make me a co-host?
right. Let me do that now.
Just so we have some options.
Okay, done.
Yeah. Okay. And then, yeah, when Andres gets here, also make him a co-host, just in case your internet goes out. Someone is
Yeah,
left hosting.
no,
Yeah.
no problem. No problem. Okay, I guess I can start, but I will turn my camera off just in case the Wi-Fi is not fantastic. Um,
So far, it's been okay. Um,
all right, sounds good.
yeah, and Andres is here now, so we
Oh
can.
yeah, let me do it. Hello, Andres. I'll just make you co-host.
Hello.
Thank you for joining.
Okay.
All right, so I think I should start. So hello everyone. Welcome to this Rubin Science Assembly. Today the topic is weak cleansing with Abell 360. My name is Shenming Fu. I'm a part of the Rubin Community Science team. Yeah, so today's agenda. So first, let me just quickly go through some announcements, and then I will talk about the background of Abell 360, including the commissioning work, the desk paper, the rest sequence, and weak cleansing. Then after that, I have two tutorials to show you. The first one is about the rest sequence of the Abell 360, and then the weak cleansing for Abell 360. So those two tutorials, they are related to each other. The first one is shorter, the second one could be longer. But if you have any questions, just feel free to ask. You can raise your hand or post in the Zoom chat. Okay, so announcements. First, the operation had begun. So you can find the official announcements on the forum, and then you can find the commissioning updates in the forum news. You can also use a tag called Early Ops Update in the forum to check the news. And then the LC at Latin America. So the meeting is December 1st to 5th. It's in Mexico City. So you can find more details there. Then double S 247 winter meeting. It's January 4th to 8th next year, early next year in Phoenix. So there are two sessions related to Rubin SST. The one is on January 4th. So it's about data access and analysis with the analysis of DOE Vera-C Rubin Observatory Workshop. And then January 7th, so this is a special session, new science results from SDOE Vera-C Rubin Observatory. January 7th. Then upcoming Rubin Science Assemblies. So next week, November 20th, that's dropping office hour. You can come and ask questions. November 27th, that's American Thanksgiving, so no assembly. December 4th, that's dropping office hour again. And then December 11th, that's a presentation about updates to Rubin's early science program with Lin Guy. Okay. Introduction to users committee. So user committee is charged with soliciting feedback from the community about the Rubin data products and science platform and recommending improvements in their twice yearly report to the Rubin operations director. So if you have any feedbacks, just let them know. You can find their website and find the reports on the forum. They have two formal meetings, and then you can contact them through email or just through the forum. Just let them know if you have any feedback. Then link frameworks. The mission is to enable scientists by developing scalable and productionize the software algorithms in collaboration with the broader community. So they have office hours. You can go to their sessions. Those most Thursdays, 1 p.m. ET or 10 a.m. PT, 7 p.m. CET. So they also have a link. They have a Zoom to for you to join. And the projects, there are a lot of projects, catalog storage, analysis, data and time series, photo Z, shift stack moving object detection, time series, machine learning, and general purpose tools. So take a look. Okay. So those are the announcements. Now let me start to talk about Abell 60 and tell you the story about that. So all started from early this year. So we have a Galaxy cluster commissioning team led by Anya van der Linden. And the goal is to pick a Galaxy cluster to test the cosmological analysis, especially weak lensing. So then we find Abell 60. It's a Galaxy cluster covered by data preview 1, the DP1, with sufficient observations. It's actually in the SV38 field, the low ecliptic latitude field. So it's a massive cluster, and the mass in SE 500 is about 6 times the 12 or 14 solar mass, and it has a median redshift about redshift 0.2. So that means it can provide sufficient lensing effects. And so that's the reason why we picked this cluster. There's some other clusters, but they're not ideal at this cluster. So when we talk about this cluster, actually, you can take a look at the figure at the lower right. So this is, you can find more details. There's a tutorial 103.6 built by Andres et al. For making this figure. In the center is a big central galaxy and some other this yellow orange-ish galaxies in this cluster. Then various tests have been done on this cluster using the DP1 data. So then I will talk about those tests. So, okay, I just saw something in the chat. Oh yeah, thank you, Andres. No, Andres just posted the link to this tutorial about making this color image, so you can take a look. Yeah, so so the different researchers, they did different tests on data. Sorry. So they write down many tech notes to record what they did. But you could find many of those tests are related to weak lensing and shape measurements. So the first one is about the photometric redshift, and the next few are about the PSA measurement, the shape measurement. There are different ways to measure the shape and shear in the field, and this data set is just a good place, and people can test the different algorithms and see their performance. And the last one is about the surface brightness, low surface brightness feature. So there's another also a next paper been written. It's almost done and to be submitted, led by Anya. So it's about a Rubin view of Abell 60. Yeah, so now I want to just go a bit of like a bigger picture about this topic of LST and the cosmology. So we can probably summarize the oh yeah, thank you, Andres, for posting the links. So we can divide the the analysis on cosmology into maybe three aspects. The first one is the geometry of the universe, and second is matter in the universe, and third is the growth of structure. When for geometry, that's basically the distance. So we have angular diameter distance can be measured through the BAO standard ruler and the strong lensing. And then luminosity distance, usually that's the standard candle, which is the type 1 supernovae. For the matter in the universe, usually we're measuring the power spectrum using weak lensing. And the growth of structure, that's the halo mass function. So we can get that from the Galaxy clusters. You can find more details in the LST science book. And recently, there are also joint analysis like 3x2 cross correlation to cross correlate the shear and the number density of galaxies. So that can include both the cosmic shear, like weak lensing, and the clustering for the number density of galaxies. Okay, so then dark energy science calibration. So the LST dark energy science calibration, the aim is to study the dark universe and study dark energy, dark matter, neutrinos, signature of inflation. And the approach is combining at least 5 cosmological probes like gas clusters, large scale structure, supernovae, weak lensing, strong lensing. And the goal is to produce cosmological results, support the community, and then make the big data challenge and learn from each other. So you can visit to the website to learn more details, and you can also join desk to be part of it. Okay, so now let me go back to galaxy cluster and just tell you a little bit more about the background for like Rex sequence and weak lensing. So today I'm just showing you some like initial level analysis, but you can just extend those analysis into more detailed research. So for galaxy clusters, they usually show a typical Rex sequence of galaxies, like a concentration of red galaxies. When you look at them on the color magnitude diagram, we'll show them later. And then using those colors, you can select foreground and background galaxies. And background galaxies, usually they're redder, so color can be useful. And for gradual lensing, basically the idea is that the mass of the gas cluster is very, very large, so it can bend the light from background galaxies, so that can distort their images. So we can look at images of background galaxies, and through this gravitational lensing effects, we can infer the foreground mass. Usually that's the dark matter. So let me tell you a bit more about lensing. So when you think about lensing, you may think about strong lensing effect, because like Einstein rings, those are more like easy to see and more popular in those photos. And then here I'm showing you an image simulation. So if you look at the left part, strong lensing can show clear arcs like lower left near the cluster center. And then the weak lensing is difficult to see directly. If you look at the upper right, far from the center, it's difficult to see this distortion. So that requires the statistics of galaxy shapes. And then, but the thing is that the strong lensing only show up near the center of cluster or center of the lens. Weak lensing can detect mass in a much larger area. Then on the right part of this image, that's the zoom in of the top right. So researchers can measure the shape just through those apertures of those galaxies. Then they can calculate the mean shape of those galaxies. So the mean shape, the mean utility is the line on top, and the true shear is the line on bottom. So you can see they're close to each other, but not exactly the same. And the small difference is caused by the noise. Usually people would divide this lucidity into 2 components we call E1, E2. E1 is along x-axis, E2 is like 45-degree counterclockwise. We can also add into like tangential and cross direction. Tangential means tangential to the center of the lens. So the distortion, or maybe stretch caused by lensing, is along the tangential direction. And the cross direction is 45-degree counterclockwise. And if it's a circular lens, it won't cause any lensing effect along the cross direction. So the source is magnified and distorted by lensing. So we can usually use this figure to show the lensing effect. So we have a source plane, there's a galaxy, so its light goes through the universe, and as lens plane gets deflected, then observed by observer. The beta, the beta angle is the original location of the source, and theta is what we observe. It's caused by deflection, so it changes the location, and also the source will be magnified and distorted by lensing. And we usually measure the distance, this angular diameter distance between the observer and the lens, between the lens and the source, and between the observer and the source. Use those distance, we can form a quantity called critical surface density. And then usually we use a term called shear. that's to describe the shape distortion. If you consider a loop, a circle loop with radius r, then the average of that shear will equal to excess surface density divided by the critical surface density. And excess surface density here is the mean surface density within the radius minus the average along that radius. So that connects the shear with the mass, and the shear in weak lensing, shear can be measured from the main shape of background galaxies. So if we can measure the main tangential utility that's proportional to the mean tangential shear, so we can connect the main shape of galaxies to the mass of the foreground lens. So that's the general idea for weak lensing. Okay, so before I show you the tutorial quickly, I will just show you this. So let's first take a look at the image in DP1. So we actually can go to the portal and then do the HIPS map. So I will just show you this here. I think I opened it here. So what we can do is already here, but I can just show you again. So you can go to portal and then there's a heat map search. So we can type Abell 360 here, and then it will automatically resolve and give you the RA deck. And then you can also select like how big that will be for the field of view. So 0.1, for example. Then we can pick the color, different colors. So here we're using UGRI. Then if we click here, so it will just do the search and then show the image. So this is like a zoom in. This is the new result. So this is the central galaxy with a lot of those orange like red galaxies. So this is the galaxy cluster. So you can just use this tool to visualize the data. Okay, let's go back. But also I want you to pay attention. There's no clear strong lensing effect like arcs or Einstein ring in this cluster. So if you like zoom in at the top, like the left one, it's difficult to see those strong lensing effects. So you could see something here, but difficult to tell whether it's strong lensing or maybe a background galaxy or something else. So strong lensing is just more difficult to detect and to see, and weak lensing effect could be extend to much larger sky area. So it's in some sense it's easier to detect, and also the distortion is small. A distortion is only approximately maybe 10% of the ability of background galaxies. So compared with strong lensing, the effect of weak lensing is not that strong. Okay, but our focus will be weak lensing today. Let me start from the first tutorial, the rest sequence galaxies of Abell 360. So I will show you this on this Rubin Science platform. So if you go to the Rubin Science platform, if you log in, it will ask you to log in first, and it will ask you about like what version you want to use. So just use the recommended version, which is 29.2.0 now. And it will also ask you how large the computer resources you want. So just use the like maybe large. Then you can find a tutorial here. If you look at the top and click the tab for the menu tutorials and DP1 and 300 cosmology. Let's do rest sequence first. So it will open the notebook. Okay, now let's just go through this notebook. Let's start from the introduction. So we can check the rest sequence through the color magnitude diagram and the color diagram, and then visualize those galaxies in the quad images. The first thing we want to do is to import general packages like NumPy, Matplotlib, AstroPy, and then we also need LST packages for Butler to get the image, and then the TAP, the tab, table access protocol, and then for that we want to get the catalog and display. So let's just load them. Here we want to use Firefly to display the images. It's Firefly is a very powerful tool. So we can run this. So we'll have an image like this. Well, here actually, I already opened it, so you can see the galaxies, they are already marked out. But if you directly open that, you won't be able to see the image. Then Butler, so we open the Butler, then also get the TEP here. Okay, so then load data. So we just assume we know the RA-DEC, the location of this central galaxy, so we can use them as the input. So when I'm talking about this, you can also open Rubin Science platform and find this tutorial and run those commands by yourself. I'm just going through this. So we provide RA-DEC and the range, like a radius. We want to make a cone search. So we need to build a query. So in this query, we want the RA-DEC, the X, Y, extendedness. Extendedness is telling us whether it's a galaxy or a star. And then we want some information for magnitude. So here we're using C model for magnitude, uncertainty, and the signal noise, and some flags. So we want to make this query, we submit a job and just wait for it to run. Okay, so now it's completed. Then it get like more than 6,000 objects. Okay, this is the first thing. Then the second thing is we want to get an image. So we want to get a deep coed image. This the coed image. Then we provide RA-DEC and ask it to search the patches, and then in this R-band. So you all find the images, and we pick the first one, the dearest one, that image to look at. So they will tell you it's in R-band and which tract and which patch. Okay, so then we want to plot the data. So the first thing is we want objects they do not have flags, do not have flag equals to true or equals to 1. So that means those are good objects. And then we do not want we want to extend this to be 1, which means those are galaxies. Then we consider 3 bands, RAZ, to get the color. So that's what we are doing here. Okay, so then let's go to this step. So we want to first make a histogram of magnitudes, and we want to see how the distribution of magnitude and signal noise looks like. So here we are using this code. We make a histogram for those C-model magnitudes. On the same figure, we want to plot C-model versus the signal noise. And mark where is the signal noise equals to 5. So this figure is basically helping us to understand the depths of those images, or may say the depths in our observation. So the blue ones are showing you the histogram. So you can see the histogram just going up, and at some point it's going down. Going up because there are more faint objects, but going down means because the depths, we won't be able to detect things. They are fainter than the limit. Just here, the peak is marked by this red dot dash line. And if we look at those black points, those are the signal noise at different magnitudes. So using those plots, we can understand like at what at the peak of the histogram, what the signal noise is. And the signal noise you can see is around like 5 or like 10 or 10-ish. So those are like good detections. So that help us to know like what magnitude we can use. So like say if for R and I, if it's above say 24, that's safe. If it's too big, the magnitude is too big, then That could be too faint. Okay, so then we want to make the color magnitude diagram. So the idea here is we want to do this like for R band. We consider two colors. One is R minus I, the other one is I minus Z for those C-modal magnitude. So we plot them in its color magnitude diagram. So the y-axis will be the difference between two magnitudes. At the x-axis, we just take the first one. So then we want to set the limit for x and y. We want to add the label and also want to make lines to show the range of those red sequence. So let me just run it and help you to understand the code. So so we are making two plots. One is R versus R minus I. The other one is I minus versus I minus Z. So you can clearly see their concentration of galaxies. So those are all galaxies, and you can see concentration of galaxies at this almost a fixed color. So this one is around 0.5. This one is about maybe 0.3 or 0.25 in those two colors. So we use those dash line to mark the region of those sequence. And I also want to make selections. So we take a small gap called epsilon, and then get the red sequence galaxies within this range of color. And also we want to make a cut at magnitude, just to pick the bright galaxies. Okay, so then we want to do the selection in both color, in both the RMSI and the IMSC. So that's why we use this and equal when we go through the colors. So use two colors can help us to improve this selection. It's better than using only one color. So now we can see this in the color magnitude diagram, but we can also do color diagram and see how the galaxy look like in color diagram. So we are still using those two colors. One is R minus I, the other one is I minus Z. So we show those two colors and make a scatter plot. Because earlier we also make selection for red signal galaxies, so we can also visualize those. And then we make lines for the two colors for the red sequence. So then we can make this plot and also set X and Y. So earlier we can see the red sequence in RMSI is about 0.5, and for IMSZ is about 0.25. We can make this plot. The select red sequence galaxies will be near the center of the scatter, and the blue dots is showing all the galaxies, and they can have different colors and in this range. We can also use other colors, maybe for example, RMSI versus R minus C, or maybe use G band. And using different color combinations, we can see different distribution of the color. And the color diagram is very useful to select different types of galaxies. Now here is just a simple demonstration. Okay, so now since we get the red signal galaxies, we can try to explore more for those red signal galaxies. So the first thing we can try is just look at them on the sky. So we can make a scatter plot because we know the RN deck. And for the selected red signal galaxies, plot them and use their magnitude as color. And we can see how they look like. So then we got an image like this. So you could see there's a lot of bright galaxies near the center. And if we go further out, the galaxy became fainter. And you can also see some clumps. Near center, there's a concentration. And here on the right seems to be another clump. So we can still see some kind of uneven distribution of the galaxies. This is the first thing, the 2D galaxy distribution. But we can also think about that in 1D. So for example, we want to show the number density of red signal galaxies as a function of radial distance. So that's in 1D. When we say density, we can consider the number of galaxies per unit area. So we can just divide the number by the area. So here we can use I should try to get the separation between each galaxy and the central galaxy and turn that distance into Archimedes. Then we can divide this radial distance into, for example, 6 bins, and then count the number in each bin. Then we want to calculate the count divided by the area, those annular area. Then we can make a figure like this. So in each radial distance, we can have the density, and the density going down after we going further out from the center of the cluster. And then we can also make the histogram. So we can plot histogram of the resting gas in different band. And this is actually similar to luminosity function because the member galaxies, they're almost at the same distance to the observer. So here we can make histogram. We get the C-model magnitude in different bands for those selected resting galaxies. And then we get a plot like this. So you can see in R and Z, they have this. So at low magnitude, there are not many galaxies, but it's going up maybe around 18 something, 18, 17 magnitude. But this increase happened at different magnitude for different bands. Okay, the last thing is we want to try the quiet image. So first we want to display this quiet image and set the transparency to 100. So we will see what happened here. So in the Firefly viewer, you will see this quiet image, and we just skip the mask, so you can see this clean image. But you can also open the mask and see those masks. Then we want to overplot the objects. So what we are doing here is first to get the boundary, and then we want to get the maximum x and y, and we want to remove the galaxy that are too close to the edge to help with the visualization. Then we just plot the xy through AFW display dot. We give a marker as circle in red and plot them. So here we have a screenshot, but I can also show you how they looks like in the Firefly viewer. So you will see something like this. So you can see those large like galaxies, they're selected. If you see them in color image, you will find they are red or orange galaxies. And then those are also big or sort of red galaxies. We also have many small galaxies. Those are background galaxies, but they are not selected. And also you can see near center, there higher concentration or chiral density of those galaxies. Okay, so this is the end of the first tutorial. Okay, so now I will switch to the second tutorial. I opened it here, but I also want to show you how to open the tutorial through the tab. Yeah, before I start, if you have any questions, just let me know. I can maybe pause a few seconds.
I have a question.
Sure.
And it's more general, but let's see the signal to noise ratio you calculated in the query, and the extendedness you calculated in the notebook. And I'm just wondering, you could have done it either way, and I'm just wondering which way is more efficient, query or notebook generally.
Extendedness, I would recommend you get that directly from query. Signal noise, I don't remember if it's included in the query in the table, then you can make the query. If it's not included, you can just calculate that.
Yes. Okay, but isn't it like you calculated in the query?
Yeah, because I at that time I don't remember. Maybe that's not in the table, so that's
Yeah.
why I calculate that. But if now it's included in the table, then you can directly make the query.
So I'm just wondering which is more computationally effective to do
Uh,
in the query or then calculate it outside, because I've done both.
Oh, yes, that's a good question. I actually don't know the answer. You might have to test.
Neither do I.
Yeah. Yeah, thank you. That's a good question. We need some tests for that. But usually we don't recommend a lot of the computation in the query, because query can be slow.
That's what I think, but I'm just not sure.
Yeah. I guess you can maybe try like a simple test, not making a big query, just say a small range of sky, a small cone search. Then you can compare the difference between the two methods. I guess the difference will be small when the region is small on the sky. But if you search for a large region, like say 0.5 degree or like 1 degree cone search, then the difference can start to show up. Yeah, thank you for the question. Oh, I saw another question from
Yeah,
Abby.
this is Abby.
Thank you.
Hi, Shenming. I had a question that I saw you plotting R minus I versus I in the color diagram.
Right.
And, so R and R minus I are correlated through R. And I was wondering if you did the plots a little differently, like R minus Z versus I or things like that. Would that make any material difference?
Yeah, so if we do R minus I versus I, it's still similar. If
No,
we
R minus I, yeah, but R minus I versus Z or R minus Z versus I.
R minus Z, we will also see this red sequence, but just a different number.
Yeah.
Because yeah, R minus Z will be I minus Z plus R minus I. So that would just shift the red sequence.
Oh, because it's only there as.
Yeah, the reference sequence almost they fix the color.
Yes, I understand that, but
yeah.
I think it's cleaner to plot it against a third magnitude.
I think that's fine. You can because the x-axis is just telling you how bright that could be. So it can be RIZ any
Okay.
yeah. And also those galaxies are when we see reference sequence, we can think they're all in the cluster, so they almost have the same distance to us. Yeah, so you can use different combination of color and magnitude for this plot.
Okay, yeah.
Yeah, I think so. That won't change the shape a lot. The main difference will come up in the color plot. If you use different colors, then the color plot will look quite different.
Yeah.
Yeah, then a very nice question. Thank you. Okay, so now I guess I can go back to this tutorial for recleansing. So in this tutorial, we'll go a bit further. The first part of this tutorial is similar to the red sequence tutorial. Basically, we want to find the red sequence and use red sequence to separate background and foreground galaxies. And the foreground galaxies, they won't be affected by gravitational lensing, so they don't have a lensing effect. We only need the background galaxies. The introduction part is similar to what I told you before, but I just want to highlight this. So you might also hear about other terms like cosmic shear or galaxy lensing. Because lensing can happen between galaxies or when light pass through the large structure of the universe. But compared with galaxy lensing, cosmic shear, cluster weak lensing is generally about 1 magnitude higher, so about 10 times higher than galaxy and cosmic shear. Yeah, so then first, again, we import the packages. Here we still need the same ones for SST, for display, for Butler and TAP. We also need some general NumPy, Matplotlib, AstroPy, SciPy for our analysis. And again, we use Firefly for the visualization. So Butler, we need to get that to find the BP1 data, and then TAP for getting the catalog. Again, we start from the BCG array deck. We give the array deck. Also, we want to pick a band for the shape. Now here we use I-band, but actually we can also use R-band. You can try this after this talk and see if you get a similar lensing effect. R-band and I-band, they're common in weak lensing analysis. And the main reason is that there's a balance between seeing and the sky brightness. So another reason is this differential chromatic refraction. So in R-band and I-band, this effect will be smaller compared to bluer bands. And then we can basically use those bands to get a better estimate of the its shape before the atmosphere. Okay, so again, we are making a cone search here. We need a bit more columns. So basically, we want not just the coordinates, the photometry. We also need shape measurement. So here we're getting E1, E2, sigma flag from this HSM algorithm, and then also blindness. I'll make the query here. And that will take a bit longer because we need more columns. So let's just wait a few seconds and see if it works. Okay, so now we get the data and let's see how many objects we have. Okay, so we now have much more objects, and also this is because we searched for a larger region of the sky, and also 0.4 degree. Okay, now let's get the coed image. So it's similar with Spatler to get a coed image. We pick the first one, and again it's in I-band. We want to shield it and then set the transparency to be 100, so we won't see the masks. Oh, sorry. Seems like maybe I should try this again. Okay, maybe I have to close it and just refresh it. Okay, let me try if I can open it again. Oh no, it's not allowing me to open that. So let me just close this and reopen it. Let's see if it's working now. Oh, it's not working. So I guess I have to maybe restart the kernel. Okay, let me try again. Okay, now it's working. Okay. I think it's also possible to move it here so we can see it now. Okay, so let's just go through the step again, sorry. Then we go through the step we have before and we have to make the query again. This query would take a couple of seconds. All right, so then let's just turn that into the table and then check the number of the objects. Yeah, the reason I want to have a bigger scatter area is that we can show how the lensing effect change with the radius, bigger area. Okay, so now we get the coed image. I want to show it here so you can see in the Firefly how that looks like. Also, we want to pick the central galaxy. So we know a deck of the central galaxy. We want to turn that into the coordinate in pixel. So using the WCS, so we can then use a dot to show this. So we can see this orange circle around the central galaxy. Okay, so now we want to get the background galaxy. So earlier I mentioned the red sequence galaxies. Those are red galaxies. They're the oldest and the reddest in the cluster. That's just caused by evolution. And then galaxies, they're rather than red sequence, they're likely at higher to be at higher redshift and more redshifted, so they can be candidate background galaxies. So we just pick galaxies that are rather than red sequence. In practice, people would also use something called the photometric redshift to identify background galaxies. But here we just use a simpler method. We use tanness and color to pick those background galaxies. So we want to use this called reference extendedness to get galaxies. So use 1 for extended sources, not 0. There is for point like. This is from the reference band. And it's based on difference between PS magnitude and Z-model magnitude. The difference, if the difference is small, then it's more like a star, but if it's big, that's more like a galaxy. We use RIZ band, and then we pick the ones without flag issue, or also make sure the signal noise is sufficiently high. Then we can select galaxies, so we find there are much fewer objects now. Okay, now we want to make the colors magnitude diagram similar to what we did before. We use RMSI and MSC, those two colors. And we use R band, I band as the x-axis and colors as the y-axis. Then we set the label, we set the limit for x, y. Let's see how that looks like. Okay, so now you can see this concentration of galaxies in this RMSI and also in MSC. But if you try other colors, you also see concentration. Okay, so now let's select the foreground and background galaxies. So we already see concentration of galaxies 0.5 for MSI and maybe 0.25, 0.3 for MSC. We want to select them out. For red sequence galaxies, we want to just select the bright galaxies. For background galaxies, they are usually faint, so we also make a cut at the magnitude. So we are setting the mean for mean magnitude for background and max magnitude for the red sequence. We want to select them out using a similar method we showed before and select the background and the red sequence galaxies. And also we want to visualize them. So after a selection, we just use different color for the marker and show them. So you get images similar to what we get in the previous tutorial, but here we select red sequence galaxy, those red points and bright points, and then blue ones are the background galaxy we selected. Those are redder than the red sequence, and they have like fainter magnitude. So we just use 2 colors to do the selection because 2 colors can give us a cleaner result than just using 1 color. Okay, so after we get those, we can just plot them and see how their coordinate looks like on the sky. We have this image. So you can see those red ones, those red sequence galaxies, they show a concentration in the center, like a galaxy cluster. But for background galaxies, they're almost uniformly distributed. So then in deep quiet image on the right, we can do the similar thing. We just get a boundary first, and then we get the max and the mean of this range, and select galaxies. They are not too close to the boundary for visualization. So we can do this for the background galaxies. So you can see those blue ones, blue dots. So you can see those galaxies. They're small, much smaller and faint than the foreground galaxies. We can do the same thing for the red sequence galaxies. So you can see the red circles. But definitely, those galaxies, they're brighter, larger. So there's a lot of galaxies in the cluster. Okay, so finally, we will do some line analysis. We are using this HSM shape measurement. It's available in the catalog. It's based on the second moments of the flux distribution of those galaxies, and they're corrected for the PSF effects, the atmosphere. Then for adjacent shapes, we can divide that relativity by 2 to approximate the lensing shear. And there's still some bias between this measured shear and true shear. That's caused by different effects, and there's a calibration called shear calibration. But actually, that's beyond the scope of this tutorial. So here we just study the mean shape as like a proxy for the shear in this notebook. So we can get the this E1, E2, those are shapes correct for the PSF. Then we want to do some selection first. So we want to make sure the repeativity is not too big, because noise can be very big, but we want to remove things that are too big, too noisy. We want to select things they have smaller sigma. That's basically the uncertainty, and then they don't have like flex equal to true. There's no issue, and then blendness, which means how the galaxy is affected by the neighborhood. I also want it to be small, so the measurement can be good. So we select those for the background galaxies. Then we do want to do some rotation because we mentioned earlier, lensing effect. They have this elongation along the tangential direction, and along the cross direction, there's no lensing effect. So we want to calculate the shape along those two directions through this transformation. We can use HLPy to first get the coordinate and then calculate the position angle, because this transformation is like a rotation that need a position angle. But in HLPy, the position angle it's starting from north, so we want to plus pi over 2 to get this right to the conventional definition of the position angle. Then we can calculate the ET and E cross, those two repeativity components. We also calculate the separation. Okay, so sorry. So first we can make a histogram for the repeativity. Now we have ET and E cross. You can see very interesting. For the E cross, this distribution, the mean is slightly bigger than 0. For the E cross, the distribution, the mean is just at 0. So mean shape is telling you whether there's lensing effect. So you can see there's lensing effect in the tangential direction. And to visualize this more easily, we can compare the difference between those two distributions. So we can just calculate the difference. We are going to get a figure like this. So because those two histograms are like maybe Gaussian or similar to Gaussian, so we'll have a dipole shape if we compare the difference between those two histograms. So this can kind of help us to see the difference between the two. The next thing is we want to bind the radial distance, because we know the radial distance. We set them into different bins, then we calculate the mean shape in those radial bins, and then we see how that looks like. We want to also add error bar. So here we just use statistical error. So basically we calculate the standard deviation divided by n, square root of n. N is the count in that bin. So mean cause of the error is from the shape noise, the shape dispersion of galaxies. There are also other contribution of noise, for example, the large scale structure, but those kind of noise is much smaller. So we here just use the statistical error. Okay, then we can get this plot. As you could see, the tangential direction, the mean shape, it's about 0 and extend to very large radii. But the cross direction is fluctuating around 0 and it's close to 0. So basically, it's just it's similar to what we expected. And the lensing signal is stronger near the cluster center and it's going down. And along the cross direction, the mean repeativity is close to 0. There's no significant systematics. So if you have deeper observations, like more galaxies, and if you combine or if you combine many clusters, we can get a better result. We can reduce the error bar. So you can also try this tutorial by yourself and also try a different color and redo this, you should be able to see similar landing effects. Usually R and I are good bands for this analysis. Okay, I think that's it. Just let me know if you have any questions. Thank you. Now you can also type the question in the chat. Oh, yeah, I think oh yeah, I think Bob just mentioned. Thank you. Okay, so if there's no more questions, I'll just stop sharing and also stop recording.